So thank you, Dr. Srikanth, for giving me this opportunity to talk on Wi-Fi location. Location is a very, I think this is the most breezy part of the entire day because we are all users of location in some form, not Wi-Fi location actually, but outdoor locationing has been a great hit, right? We all use GPS-based locationing systems and it has become an integral part of our lives, right? But the story of indoor locationing is very different. And it still remains a very unsolved problem because of several challenges. We are going to talk about some of the challenges in Wi-Fi based locationing solutions today, right? So the focus of the talk is going to be more about the, the factors affecting the, so it will be mostly factors affecting the accuracy, right? When it comes to indoor locationing, in outdoor location, even if you are off by a few meters, a couple of meters, or even 5 to 10 meters, it is still okay, right? We will still be on the same road. But when you are in indoor, even a half a meter or 1 meter inaccuracy could place you in a different floor altogether, right? Or in a different room within the same floor, right? So that gives a very awkward kind of feel to the user, right? So in terms of indoor locationing, they are classified into actually two different use cases. The first set of use cases is mostly positioning and proximity use cases, which are mostly user centric, whereas the second class of solutions are all infrastructure based, where an event management location like this would want to know how many people have checked in into the hotels, or how many people are there in a certain conference room, right? Or emergency solutions where government regulations like E911 require that a particular user in distress be reachable within a few meters of accuracy, right? More importantly, in the case of Wi-Fi, the entire thrust of locationing has come from the last point, the access point geolocation requirement in 6 GHz operation. So that has actually provided the thrust for most of the locationing solutions that will crop up in the next few years, right? But what has happened over the years is that the infrastructure providers did not see any value in user-centric locationing. So, of course, but every locationing solution would need support from infrastructure. So what has happened is there has been a huge disconnect between the user required applications and the infrastructure provided applications. So indoor locationing has become more like a, did not take off as much as it should have, right? But with the Wi-Fi 6 GHz operation, the access points are necessarily required to locate themselves with respect to each other, right? And they cannot escape because otherwise they will not be allowed to operate in the 6 GHz, right? So let's take a brief look at the Wi-Fi based locationing evolution. So traditionally most of the locationing in Wi-Fi has been based on RSSI based solutions which still exist today, but it has moved to RTT based, that is round trip time based locationing with the release 2016, right? But the problem with there are a few problems with 11MC. Mostly security based, so the clients were not refusing to implement FTM based implementations because the client's privacy is important, right? So nobody can spoof a client's location, right? So with 11AZ, that security problem is solved, so we will see more uptake in 11AZ based solutions. So currently we are in the era of 11AZ, which is ratified very recently. And the upcoming next level of accuracy is from the 11BK that is supposed to be addressing the 320 megahertz channel, which is very close to the UWB, which is based on 500 megahertz based channel width, right? Of course, in all the RTT based locationing, we can see that the accuracy depends on the channel width. So increasingly we would see more and more channel widths being supported in the locationing protocols, right? How is ranging done? Yeah, as I mentioned, it's RSSI based or even phase based, but the second option is slightly expensive because you need an array of antennas at the access point, right, to do any phase based estimation. And the cheapest and the most accurate would be the time of flight based measurements, right. Now of course positioning is not just about ranging. Now all these techniques are just ranging, that is they just measure the distance, but positioning is something very different. That is, you need to locate an object or a person in 3D space, right. That requires an additional technique called multilateration, which is like kind of complex computationally as well as in terms of software or GUI implementations, right. But we will not talk about positioning today, we are just talking about ranging. So coming to the fine timing measurement, this is the protocol essentially, right. So you have an initiating station which could be a client, or in the case of AFC this could be an AP also, and we have the responding station which is typically the AP, right. So the initiating station is the one which wants to locate itself with respect to the infrastructure. So there is an exchange of initial FTM request. After that, following the request, if the AP is has the capability to do the ranging, it will trigger a series of, if you can see, there is a series of measurement sessions going on here. It's not just a single exchange, right. So over this series of exchanges, the distance is measured as the time difference between the signal that is transmitted and received back, and the initiator makes a quick distance calculation based on the time difference of the signal and the speed of light. Of course, these are electromagnetic waves, so they travel at the speed of light. So this is why it gets its name, round trip time RTT based location, right. So this is the protocol as such, but what are the challenges in this protocol? Of course, the accuracy of this protocol depends on the granularity at which you are measuring those time steps, right. And that is directly proportional to the channel width, because the higher the channel width, the more the sampling rate and the accuracy at which you can measure those timestamps. And of course, if there is interference, you will see a lot of packet drops, and which will result in poor accuracy. And more seriously, what we have observed in our measurements is firmware calibration, right. We will get into a little more detail on this a little later. Why is calibration required? And this is one of the biggest sources of inaccuracy in FTM based solutions. And then different clients have a wide range of firmware calibration errors. And secondly, the FTM protocol itself allows a lot of flexibility in terms of how many bursts you can use, and how many repetitions you can make for the request, or how many samples you are going to average the location, right, range. So because of all these differences, different clients behave differently, offer different levels of accuracy, right. So here are a few performance results that we have conducted. So there is this is a typical enterprise setup where we have cubicles and conference rooms with glass doors and plywood partitions, right. So we place the AP and we take measurements in different RF locations where you will see both line of sight coverage as well as non-line of sight coverage, and we have tested with different kinds of partitions, ply, brick plus ply, even across floors, that is with a concrete slab in between. And we have tested with Google Pixel 6 and a different Zenfone 9. I'll present the results for that. And we have used two different channels. One is the channel 36, most commonly used 5 GHz channel, and channel 52, which is a DFS channel. So that we used so that we can examine the performance under low interference scenarios, right. And for each measurement we have sampled over 1,000, averaged over 1,000 to 2,000 samples. So what the first challenge we have seen is that there is a deviation at the starting of the FTM session and at the end of the FTM session, right. The deviation is high, mainly because the protocol in the first packet, the time difference is not available for the initiator, right? So that results in a lot of error, and even that's not available in the last packet also. So during a single FTM session, you will see a lot of deviation in the beginning and the end of the measurement. So we have to filter out. So you just do 2 sigma filtering on the data points, right? And the first study is on the channel width. If you can see here, this is 6 meter measurement, and you can see that 80 megahertz channel width gives the closest, and 20 megahertz gives the highest error in this case, right? But this is in a line of sight scenario. But when you go to non-line of sight scenario, the story is slightly different. So when you are in a non-line of sight scenario, there is a lot of multipath, which results in delay spread. And when the channel width is low, delay spread is less, right? So we see that 20 megahertz gives a better resolution, or better estimate than the 80 megahertz, right? And the effect of interference, the second factor is the interference effect. What we can see here is that the channel number 36 had huge interference with 20 APs, whereas channel 52 is a relatively free channel, right? So you can see that deviation is higher in channel 36, but surprisingly RTT performs really well. So the actual distance was around 12 meters. So even with interference, there is just 1.5 meters of inaccuracy, which is really good. So if you see this, if you try to measure the same with an RSSI based technique, you would be way off in an interference scenario like this, right? And then let's briefly take a minute in understanding these offset, because this is the major source of inaccuracies both at the clients and the AP side. So how do we measure the timestamps, right? So the timestamp has to be measured at the antennas. So at exactly the time at which the signal departs from the antenna and the time at which it arrives at the other antenna, right? But antennas don't have a measurement technique. They can't record timestamps, right? So the timestamp is put much ahead at the MAC layer itself, right? Now how do we put it? The chipset vendor has to estimate this delta from the MAC to the antenna, right? And this is a very fine calibration exercise. Now there are 4 different components, such components in this entire, and mind you, the forward delta and the backward delta are not the same again, right? And this differs even if you are taking 2 devices from the same vendor, these deltas could still differ, right? But of course, we can average, get to average values of these deltas. But so this, and how does this have a huge impact? Because in 1 nanosecond, light travels about 1 feet. So you are 3 nanoseconds off in this timestamp, you are already 1 meter off in your accuracy, right? So this has to be very carefully calibrated to get good measurements. So we can see that effect here, right? So this measurement is from with a Google Pixel client with one of with an AP, right? And turns out the Google Pixel was very well calibrated, because Google is very much bent on their locationing solutions, right? But our own AP was not calibrated, and it was only calibrated for the 80 megahertz operation, assuming that FTM will use only 80 megahertz, right? But if you test it at 20 and 40, you could see way off. That is, the measurements are around 75 meters off for 20 megahertz and 40 meters off for the 40 megahertz case, right? So calibration makes a huge difference. So then we fought with our chipset vendor. I asked them to calibrate and give. Not all clients will operate in 80 megahertz, right? So then they corrected it, and then we can see the good results here. And this is the effect of client chipset. Comparison between Zenfone and Google Pixel, right? So we can see that Google Pixel is a very highly calibrated device, right? And Zenfone performs very poorly. I mean, it's not way off, but it's compared to Google Pixel, its performances was really poor. So we actually tested with Samsung also. The results are so bad that I don't want to present here. I don't want to, bring down Samsung's image in any way. But so, yeah, so the 3 nanosecond error, results in almost 1 meter of error. It's a problem with any kind of RTT, not just with 11MC, right? But, and multipath reflections, if you can see here, you will see different peaks. One peak is, gives you a different distance value than the other peak, right? Now you are confused which one to take, or you have to take average, right? And the accuracy definitely depends on the channel width, and with 11MC you can only have 80 megahertz, right? So you can only get so much accuracy. And the major problem for the client-side implementation of FTM has been that FTM does not provide any encryption or any protection. So it was an open frame transmission, right? So these are the issues with MC which AZ attempts to improve. There are huge, there is a plethora of improvements that AZ provides over MC, but I'm not going to detail in any of these. Only thing is that security is provided by 11AZ. And in 11AZ, multiple clients can connect to the AP and do multiple parallel FTM sessions, which is not possible in 11MC. This is important in a hugely dense scenario, right? Where in an events like this, a lot of people want to locate themselves within a venue, right? Or in airports, or in malls, right? It is possible for to scale up the ability of AP to provide multiple scenarios. And important thing is on the accuracy, right? So the better accuracy that 11AZ provides is you can do 160 megahertz measurements in 11AZ, and there is a repeated LTF. I don't want to get into technicalities of this, but which improves SNR for FTM. And most importantly, 11AZ allows MIMO to be used for FTM sessions, which was not possible in 11MC. So when you use MIMO, you can identify the shortest path, which gets rid of the multipath problem. So you get better accuracy with 11MC AZ, right? Yeah, sure. Yeah. Yeah, so these are the 11AZ performance results. What we can see is that even at an close distance, so one of the issues with 11MC has been you can't measure distances less than a couple of meters, because that is the maximum limit you get with 80 megahertz. So if you try to measure anything less than 2 meters, you will get inaccurate results, right? Whereas with 11AZ, you can go up to 2 meters and less, and you get a reasonable error with that, right? And even in non-line of sight, even with 20 megahertz, you get good error, I mean less than 2 meters of error with 11AZ, right? So in conclusion, FTM is a good answer for the indoor locationing applications that we have, and with appropriate positioning techniques, this ranging can enable several location-based applications. And with AFC becoming mandatory for 6 gigahertz operation, there is a huge push from the infrastructure vendors, AP vendors, to support FTM. So we will be seeing a lot of indoor locationing applications. Yeah.
Thank you.
Yeah.
Thanks. We do have time for questions. Quick, where is our volunteers? If you can get the mic, you can. Yeah. Sai, I saw. Yeah. People at the back, if you'll have to really raise.
Thank you for the very, very nice talk. I'm glad your chipset vendor supported. Our chipset vendor gives us negative measurements, so we are not able.
No, we didn't see negative measurements. I didn't show them, but we did see.
You don't want to name your chipset vendor, right?
I mean, it's public, everybody knows.
Room, yeah.
I have 2 questions. So, do you see any impact of orientation of the device?
Yes, of course. I mean, we couldn't spend so much time to test it in all directions, but yes, antenna direction definitely affects, but not so much as an RSSI measurement would do, because remember, this is only timing based, right? So orienting the device in a different direction will only have a marginal impact on the signal strength, but not on the RTT. So this is in a way immune to such kind of errors.
So Then would you like to try 2.4 gigahertz, which would be slightly lesser error-prone to orientation than 5 gigahertz? What is your thought on that?
With,
Because you showed good results with 20 megahertz non-line of sight in 11 AC. So if you would
Yeah.
repeat the same thing in 2.4, in general, lower the frequency, orientation issues should go away. And I
yeah,
think so.
we didn't test that, but we were concentrating only on 5 gigahertz because our focus was on AFC, get to, AFC thing done. So, yeah, but we could do that, yes.
Thank you. Thank you so much.
Thank you.
Take one more question. I saw some hands. Yeah, can you get the mic to her, please?
Hi. So I have a question, very basic questions. I may sound unfamiliar maybe. Because I'm not familiar with this protocol, 802.11az.
Yeah.
So do I understand this is a location detection and the real-time application will be Google Map kind of thing?
Yeah, so this is just a ranging method, right? It's just
Okay.
for distance estimation between the AP and a client device, right? So you should have an application which will use this ranging to put that blue dot.
Okay.
So you should have floor maps, you should have the GUI to support. If you are going to do it in a indoor, if you need a 3D location, right?
Okay.
So all that is, that's why I said in the beginning that there is a huge effort other than just ranging to put a blue dot on indoor locationing.
And we have this protocol like 11A, 11AC, 11AX. So this protocol is a default protocol come along with that?
I can answer
Yes.
that quickly.
Okay.
Yeah.
So 11AZ is basically adding on top of your AC, AX,
Yeah.
and now the BE. It will add fine timing measurement capabilities.
Okay.
So with AX onwards, you have support for AZ
Okay.
automatically by the standard.
Okay.
Yeah.
Yeah. Thank you.
Oh, thanks, Vijaya. Yeah.
Thank you.